Okay, since you're directed to use L'Hopital's rule here, we have to get this in the form of a fraction. Okay, right now we've got infinity minus infinity. And a typical technique for getting this into a form where you can use L'Hopital's rule is to multiply this fraction, where I put a denominator of 1, by the conjugate of this numerator, that is with a plus sign between the radicals. The reason that helps is because in the numerator you get a difference of squares. This radical squared minus this radical squared. Of course, in the denominator, you'll just get this conjugate. Okay, so the new numerator, after you do that, is 7x minus 11. If you just subtract this squared radical from this squared radical. I didn't write the limit as x approaches infinity all the way down here, but I did write it here. Now here's some things by the way, here's a graph from Desmos that kind of convinces us that the answer for this limit is 3.5. I've graphed this function and made up a table of x's and f of x's. And as x approaches infinity, like there it is approaching a billion, it gets very close to 3.5. And actually for that next multiple of 10, it really does say 3.5. The other thing you have to convince yourself of is that for expressions like this, where we have a rational function and the degree of the numerator equals the degree of the denominator, and the limit as x approaches infinity becomes the coefficients of the highest degree terms. That should be something that you use all the time. So here's kind of proof. G of 10,000 is 0.9999. If I keep adding zeros, I get closer and closer to 1. Okay, so we'll go to the next board. We haven't applied L'Hopital's rule yet. This is a fraction. If x approaches infinity, we get infinity in the numerator and infinity plus infinity or infinity in the denominator. So this is an indeterminate form, so we can apply L'Hopital's rule. And so here we go. Here's the limit as x approaches infinity. Since it's an indeterminate form, we can apply L'Hopital's rule, which means the limit as x approaches infinity of the derivative of the numerator over the derivative of the denominator will be the same. So here's the derivative of the numerator, 7. The derivative of the denominator, I have to apply the power rule followed by the chain rule. This is what you end up with. And for the second radical, if you take the derivative of that, you get 1/2 that radical or that trinomial to the minus 1/2 times the derivative of the inside 2x plus 1. Okay, now as x approaches infinity, what are the limits of these terms in the denominator? Well, if I factor a 2 out of the numerator, just to make it a little easier to see, these 2's cancel out. And what I'm going to do to help make it easier to see is introduce this x plus 4 under this radical by squaring it. So that's x squared plus 8x plus 16. That's just another way to write what we had originally, x plus 4. And now the limit as x approaches infinity of this expression right here is the same as the square root of the limit of this thing. But the limit of that rational function, since the degree of the numerator equals the degree of the denominator, is 1. And the square root of 1 is 1. So I can replace this thing right here with a 1. And I follow the same technique over here. To make it easier to see, I factored a 2 out of the numerator, canceled these 2's, introduced x plus 1/2, the quantity squared under the radical. Notice that the limit of that radical is the same as the square root of the limit. That limit is 1, so I can replace this expression with the 1 also. And there we go. 7 over 2 is 3.5. Okay, so as x gets bigger and bigger, this original function will approach 3.5. Okay, there you go. Hope that helped. If you have any questions, post a comment.